All right, well, thank you. It's a pleasure to be here. I always enjoy coming up to the far north, or relative to where we are. And a small comment. Well, first of all, you should know that I'm actually retired from Argonne. They call me an Argonne associate. They've also called me a physicist, which is, my background's actually in chemistry. So that's their problem, not mine.
It's electron physics.
Yeah, well. How many people are chemists? All right. Anybody recognize that? That's a real molecule. It's something that I did a high pressure study on when I was at Los Alamos, and it's the high explosive pentaerythryl tetranitrate, otherwise known as PETN. So I'm starting my lecture off with a bang. Okay, that's the logo for GSAS-II. So you'll see it scattered all around, and when you install GSAS-II, it shows up on your directories and all that sort of stuff. But that's what that is. It's sort of a reminder of my time in Los Alamos. It was an interesting experiment, especially from the safety point of view. What I'm going to cover is a little bit of history. It sort of complements what Joel said. Talk about a couple of extreme examples, one of which he actually talked about, which is the protein, but the other one I think might be a bit of a surprise as well. I will then deal with the math, or some parts of the math for Rietveld refinement, which basically builds on what Joel talked about earlier. And then go through a worked example, which is one of the tutorial examples for GSAS-II. And this is an example that's been around for 40 years or so, maybe even close to 50. So it has a long, illustrious history behind this particular sample. So without any further ado, let's get it to go. Yeah, all right. First of all, Hugo Rietveld, he's here standing next to his neutron powder diffractometer, which given the times might have been in operation with the shutter open and all that sort of stuff. This is back in the middle 60s. He wrote two papers. This one was a very little short note, all of 2 pages, that described the piece of software that did this particular calculation. And the second one is a more elaborate one that talks about the method and the mathematics behind it. And what he wrote originally was a pair of programs written in a funny language nowadays called ALGOL. He then translated this into Fortran and distributed that to whoever would ask him for a copy of it. And it would take, everybody know what an IBM card looks like? Okay, they're sort of cards about go big, and the code takes about 2 boxes of cards, something like that. And what he described was basically a multi-parameter, non-linear least squares curve fitting procedure to fit the curve, which is a powder diffraction pattern. That's very, very important to remember that this is a curve fitting exercise. That means everything that is used to describe the peak shapes, the peak positions, the peak intensities is actually part of the model. The peaks themselves are part of the model used to fit this powder diffraction profile. Reflection intensities have no separate existence on their own within a powder diffraction pattern because it's part of the model. The reason why I emphasize this is if you go back and look at the history of the Rietveld refinement method, there's going to be a whole bunch of papers that go through a bunch of controversy about it back in the middle 70s and early 80s, where the authors basically got very confused about that point, and they were busily counting reflections and all that sort of stuff, and it was completely misguided because this is a curve fitting exercise, has nothing to do with single crystal reflections. Okay, basically, every point in a powder diffraction profile is considered to be the sum of the reflections that contribute to it. And as a consequence, the refinement minimizes the function, which is the weighted differences between the observed intensity and the calculated intensity squared. This thing here is the function that's actually minimized. And so the least squares process consists of taking the derivatives of this thing with respect to all the parameters associated with it and creating a least squares matrix and so forth. Statisticians will call this thing chi-squared. That's its official name. A lot of people get confused and call this thing chi-squared. The official name is reduced chi-squared, in which you take that minimization function and divide by the number of degrees of freedom. So the literature is a little confused about this because people think this is chi-squared. No, it's that. This thing is sometimes called goodness of fit, which is, I'm not a fan of it, but that's what they call it. Okay, let me see if I can get it to go to the next slide. Yes, here we go. Well, where did I start with this game? Well, I was a postdoc at Oxford, working for Professor J.S. Anderson, trying to do electron microscopy, and I wasn't very good at it because my eyesight wasn't that great. And this is before I was wearing these things. So Tony Cheatham walked into my office one day, and he was also a postdoc at the same time, and asked me whether I'd be interested in doing a neutron powder diffraction experiment. And I said, sure, anything to get away from the electron microscope, I suppose. So we, and I'll talk about the samples in a minute. So we ground up these, made these two samples, and they were about this big. Yeah, something about that big each. And took it to Harwell, which was just down the road from Oxford, about 35 miles, to the Panda, to the Pluto reactor, which is this. And by the way, the shell is still there, you know, off in the distance. And we did this experiment on something called a Panda diffractometer, which had multiple detectors at a high takeoff angle off the monochromator, and did this experiment and did it at wavelength somewhere around 1.5 angstroms. The scan was 50 minutes per degree. It took 3 days to collect the powder pattern for each one. And this is done at liquid helium temperature, so we had to go back every once in a while and refill the cryostat. And it was, I believe, my recollection isn't so great, it was somewhere down in this pit next to the reactor. Yeah, that was the scan. What was the sample? Well, first of all, the Rietveld program version that I started with was one that Alan Hewitt had modified to make it do anisotropic temperature factors. And this is his manual, and I still have this book. And it used only Gaussian peak shapes, and there was an incorrect asymmetry correction built into it that was created by Hugo Rietveld. But this was 1973. What's that, 50 years ago? Something like that. Okay, what did it run on? It ran on this thing, or at least the equivalent one at Oxford, which is something called an ICL 1906A. ICL is the English equivalent of IBM. This is its characteristics. It's not very big. It ran on an operating system called George III, which is an American I always thought was slightly amusing. It produced a megawatt of heat, and this room that it sits in would be about 4 times the size of this room, something like that. And it had about less power than this thing, much less power than this thing. it took probably a couple of hours to do a Rietveld refinement calculation each time. What did we do with it? Well, interestingly enough, it was these two compounds, titanium niobium oxide, TiNB207, and this other one, which is Ti2NB10O29. This one's monoclinic, C-centered monoclinic. This one is A-centered monoclinic, okay. And this one is A-centered orthorhombic. These are funny little structures which are so large in 2 dimensions and real thin in the third. So the parameters on the atoms were just X and Y, or X and Z, I don't care how you call it. And the other direction is fixed at either 0 or half. What we were interested in is to determine where the titaniums and the niobiums were. And since this is neutron scattering, it's actually dead simple to tell the difference between the two of them, because titanium has a negative scattering power and niobium has a positive scattering power, so it's easy to distinguish between them. So here's the powder patterns. This one's for this one, and this was for this one. The real problem was that this had 600 and odd reflections, that had 800 odd reflections, and Rietveld's code would only handle 300. And the computers were not big enough to simply make the arrays 800 by 800 or whatever it is. So I had to modify the programs in order to be able to do these larger structures. These two structures were in fact the largest structures done by powder diffraction for quite a long time, simply because of the size. So now, fast forward 20 years, 50 years later, like last year or maybe the year before, I got this email from someone who said, how would you like to have your name on this paper? And what they described is the stuff that could be the next battery material, because it turns out that lithium likes to go into these two structures. And so my word about this is that if someone asks you why you're doing a particular scientific experiment, this is evidence that you just never know what it's going to be good for. But you do it anyway, because the paper, that new paper, their reference to the structure is in fact to our publication in the Proceedings of the Royal Society in 1974. Probably doesn't appear in anybody's citation index, I can tell you that, because it's way too long ago. Anyway, a couple more examples. One's the biggest, and the other is the fastest Rietveld refinement result, or the fastest experiment. Remember I told you about 3 days apiece for those two experiments with neutrons? So the biggest one, why do proteins? Well, why not? And by the way, if you ever look at protein structure determinations and papers and all that sort of stuff, you'll see sketches that look like this. This is sort of a space-filling model that sort of shows the sort of lumpiness of a protein. This one is a sort of a so-called ribbon diagram where you can actually see where the alpha helices are versus the beta sheets. And this is a rather big protein. And the other is, in fact, actually this insulin structure that I worked on, where it's so-called schematic, where these little coils are replaced by sausages. And it doesn't have any beta sheet structure in it, so you can't see what that looks like. These things are not small, but all the molecules are the same, ideally. And the other thing about a protein structure is it's like 30 to 50 or 60% water in between the protein molecules. And here's a powder pattern from a protein. The picture really doesn't even do justice to the original pattern, because you can see rings all the way out to the edge of the image. The image, that this position here is at about 1.8 angstroms D spacing, and between here and here there's 9,000 reflections in that powder pattern. The original basically looks like an old record, or a CD, because there's so many lines on it. Very spectacular pattern. It was collected in what, 30 seconds or something like that, let's say. This inner ring is at 55 angstroms despacing. And this feature in here in the background is because of the water in the structure. Gives you a diffuse pattern because it's disordered. And the material is a cheap, easily crystallized protein hen egg white lysozyme. It costs $100 for 10 grams. Buy it off the shelf. Fun to play with. Here's another feature about protein powder diffractions, is that they're absolutely ideal if you've got a crystalline one. Their crystallite sizes are around 1 micron, and there's no microstrain. So there's no sample broadening for all intents and purposes to a protein powder. These lines are sharper than the standards. And this is an insulin, and you notice it starts at 8 degrees. Well, I don't show the pattern between a half a degree and 8 degrees because it would be up through the next floor somewhere. They're that strong. But there is just hundreds and hundreds of lines in that pattern. So my experiment that Joel mentioned earlier was to look at insulin, and I did something that was horrifying to protein crystallographers. I took single crystals and ground them up in order to make a powder pattern. I wasn't interested in single crystal diffraction. I wanted to do powder diffraction, so I had to grind up single crystals. The amusing thing about this is that those crystals were a test crystallization that replicated one that was done on Skylab at the same time. And so the experiment was to try to compare space-grown crystals with ground-based crystal growth. And so I like to say that this is the ground test sample. And so I did this powder diffraction experiment at Brookhaven and got that pattern immediately after grinding. And for some reason, which I will not explain why, I went back and looked at that same sample again 2 days later and got that pattern, and it's different. So there was a phase change somewhere in between. And when I indexed this pattern, it was rhombohedral with this unit cell, 81 by 81 by 73. This one, after indexing, was again rhombohedral, and it was 81 by 81 by 37. That's half of that. This matches the single crystal, the known single crystal lattice parameters for this particular insulin. And so what had happened here is it simply had doubled along the c-axis. Well, that led to the next thing, which was to say, okay, let's model it by taking the original unit cell, simply doubling it, taking the two groups. It forms a sort of a trigonal arrangement of molecules, and simply having one rotate versus the other. It's a 3-parameter problem. So I solved this crystal structure varying 3 parameters, which is the rotation of one insulin group versus the other, and how far apart they are. So that wound up with a structure with more than 1,600 atoms, almost 500,000 cubic angstroms in the unit cell, and did a Rietveld refinement on this whole structure with a whole lot of restraints to keep the bond distances binding with some flat flames under control, and got a ridiculous residual for it. And you can see the structure here where the grouping in the front is rotated slightly with respect to the one in the back, about 9 degrees. And so I sent this off to my colleagues at the Hauptmann Woodward Institute in Buffalo, sent off a copy of the paper, and they came back with, "You scooped us." because they had encountered the same crystal structure in a single crystal study at low temperatures, and there's theirs, and there's mine, and they're, for all intents and purposes, the same. So what's going on? Well, the action of grinding the protein induced a phase change from pressure. They got the same structure because they put cryoprotectant around the crystal, froze it, the cryoprotectant shrunk, and induced the phase change. So it's a pressure-induced phase change to get from insulin to this double C-ax version. Okay, that's amazing. Now, fastest. In a synchrotron, and you're going to go see one sometime today, tomorrow, whatever, the electrons in the ring are in bunches around the ring, and they all circulate together at close to the speed of light. And you don't notice this during an experiment because they're so close together and they go around so fast that the pulses between one bunch of new electrons and the next bunch of electrons is in nanoseconds. So you get this pulsing of the X-ray beam, which is sort of invisible. Well, there's a mode of operation for APS in which they can take all those electrons and put it into a single bunch. And they call that single bunch mode. And the object here is that you have this single bunch of electrons going around, and it generates a big pulse of X-rays. Well, there's a beamline in which they want to do this experiment so that the X-rays arrive at the sample the same time a laser, a high-power laser, hits the sample, basically blows it apart. And so the simultaneous experiment is to try to probe what's going on in this material under extremes of temperature and pressure. Sort of a shock experiment. Not too different from the kind of thing I did with PETN, but I didn't want to blow it up. So they created a powder pattern of the test material, which is cerium dioxide, which looks like the thing over there, in a single bunch, single pulse of X-rays from APS. And they said, can you analyze this? And I said, sure. After a lot of work, because here's the powder pattern from the CEO2, just by integrating that image. And I looked at these peaks and I said, wait a minute, that looks familiar. It's the same as neutrons on a flight peak shape. So I did the math, which is here. And you really don't want to know the details, but there is a Gaussian function and a Lorentzian function. They get convoluted with a pair of back-to-back exponentials that look like that. I'll talk about that a little later. And you do the arithmetic, and you get a Gaussian function that involves something called the complementary error function. And I won't tell you what it is. You can go look it up. And then this thing for the Lorentzian gives you something called the imaginary part, that's what that is, of the exponential integral. And again, you can go look that up. But these two guys are then combined in a pseudo-void using the same math that Joel talked about earlier to create a peak shape. And it actually fit those peaks very, very well. And so here's the fit. Now, the length of the experiment was 100 picoseconds. Now you may ask, how long is 100 picoseconds? Well, think about the speed of light and ask yourself, how far is light going to travel in 100 picoseconds? If you do the math, it's that far. 3 centimeters. That's how quick this experiment was. Which is a lot quicker than that first one 50 years ago. A lot quicker. So I had to discover what the dependence of the various coefficients are. And anyway, the point is one can do crystal structures at ridiculously high pressures that are created under these conditions. So now, By the way, if anybody's got any questions, just raise a hand and ask. But I want to remind you of something. I'm deaf, so you'll have to shout, even with hearing aids. So I'm going to walk over here and listen to what he has to say.
I see the general increase in the intensity at high magnitudes has been.
That's a background. Yeah, that's basically a background. And but the angles weren't very high. If you go back to that original image, it only goes to about 30 or 40 degrees 2 theta. Okay.
The protein powders you are showing, they are isolated proteins.
Sorry?
The protein powder data you are showing, are they isolated single proteins or they are group of?
No, this is polycrystalline protein crystals.
Okay. They are.
There's not isolated molecules. This is crystalline material.
But they can have different types of proteins.
Oh yeah.
Okay. Because like lots of people here do.
Well, no, wait a minute. I'm sorry. The proteins ought to be pure, single phase. Okay. Otherwise, the problem is entirely too messy.
Yeah, that's what I'm asking.
Yes, and the thing about crystallizing proteins that I know about is if they aren't pure, they won't crystallize very well. So this simply gets over the situation where you do a crystal growth for a protein under a certain collection of conditions, and you wind up with microcrystals. That's what these are.
So if they do the crystallize the protein and that structure and this structure are more or less similar, because they will be in different states, are they different? How do the structures look at the end?
They should be the same as what one gets for larger single crystals. It's just that if you have a protein, my view of this is if you have a protein that refuses to grow large crystals for whatever reason, there's still a way to look at some details of the crystal structure based on powder diffraction. And by the way, there is a group in Greece, in Patras, that's been doing this for the past 20 years based on what I had originally started. And they have solved, I don't know, 3 or 4 or 5 protein crystal structures using these techniques. All the methods for single crystal structure determination work except for mad phasing. Mad phasing doesn't work because the Friedel pairs in a powder diffraction pattern are overlapped exactly. So there's no way to tell. Okay? Yeah. Okay, Rietveld, refinement, and GSAS-II.
Quick question. When you talked about the pressure-induced phase changes, what pressure approximately was that?
Kilobar, maybe.
Oh.
Yeah. That was for insulin. Yeah. That's just a guess. Nobody really knows. That just depends on what you get. I mean, it was literally ground in an agate mortar in its mother liquor. And that induced a phase change.
Approximately how long were you grinding it for?
A few seconds. It doesn't take very long.
Okay, just out of curiosity.
Yeah. Yeah, it was a few seconds. Just enough to make a powder out of it. I could hear them crunch as I was doing it. Anything else? Okay. Okay, whoops. There. Okay, Joel showed this equation designed by a committee. One committee member added another term, and that is this, which is a multiplier on the whole thing due to the instant intensity. And the reason that's in there is because for a neutron time of flight experiment, the instant intensity depends on the wavelength. It's a lot at short wavelengths and peters out at long wavelengths. So but everything else is basically the same. It's got all the same pieces in it. And what I want to focus on basically is this one, which is the peak shape function. Joel covered very, very well all the other stuff as to what those corrections are. Okay, some basics. I think you've seen this before, but here's the Gaussian function. The important thing about this function and the Lorentzian one is these are both normalized. And what does that mean? That means that do the integral across the peak, you'll get unity. And that property is important if you're going to get things like scale factors, structure factors, and all that sort of stuff out of the peak intensities. And in the modeling of, you have to model normalized peak shapes. This is then combined, if you convolute the two together, which one can do in a computer, but it's really tedious and expensive. There's not a known mathematical function for that convolution, apart from the name, which is called a void. So we use a pseudo-void, which is a lot cheaper, where you have a mixing coefficient, eta, and eta is determined via Thomson-Cox and Hastings. And the important thing about what they did is they made the pseudo-void equal to the void mathematically, within a few hundredths of a percent. The other thing that, the other sort of big change that was added to it is in constant wavelength experiments, there's an asymmetry due to so-called axial divergence. And this is where you're dealing with a point source and a point detector. You're dealing with a macroscopic source, a certain size. It has slits in front of it, and then there is a detector, and it has slits in front of it, and it's also a macroscopic size. And the height of the slit dictates how the beam intersects the Bragg cone. It's not intersecting as a point, it's intersecting as a line. And so it clips it at the top and the bottom. I sometimes have a figure that I show, but you can sort of visualize what's going on here. And that gives a sort of a peak shape effect to it. Anyway, this was described by Fingercox and Jeffcoat, and this is all built into GSAS-II. And by the way, there's a little bit about selection of units. In GSAS-II, and the old GSAS as well, the position of the peaks is, for 2 theta, is in centidegrees, not degrees. You may ask, well, why? Well, that's so that the UV and the W coefficients for the peak shape come out to be reasonable numbers rather than 10 to the minus 5 and 10 to the minus 6. That's all. Just makes it more comfortable to work with. Okay, sample broadening. Well, now you have to sort of think a little bit in reciprocal space instead of real space or ordinary space. And you have to ask yourself, if you have a big crystal, bigger than, say, 5 microns, then the resulting points in reciprocal space are simply the Fourier transform of the size of the crystal, which means, for all intents and purposes, they are delta functions. If you reduce the size of the crystal, the Fourier transform then gets broader, right? Everybody knows that? Yeah. So small crystals, you don't get delta functions, you get peaks in reciprocal space, and they are the same width in reciprocal space, assuming it's isotropic. Everybody with me? Okay, so then you can take Bragg's law. So what that means is that delta D star, which is this dimension, is constant. And if you do the math, that means delta D divided by D squared is a constant. And that winds up being delta theta cotangent theta divided by the D spacing. Okay, that's just simply applying Bragg's law. And eventually, if you work your way through it, you'll wind up with the Scherrer equation, which depends on 1 over cosine theta. On the other hand, if you have microstrain in the lattice, what that means is that not all the unit cells are the same size. And the reason why that happens is because you have defects inside the crystal, whatever they are. There's no identification of what these defects are. You simply have defects that make some unit cells bigger than others, or smaller. Well, usually bigger. Well, what that means is that the variation in unit cells then changes reciprocal space from being a point at the origin to something broad out at larger D stars. And that's simply because the unit cells are a different size. And the thing that's constant here is that delta D over delta D star divided by D star is a constant. Okay? And you can again work through the math, and that winds up being delta theta cotangent theta. And again, this is so based on Bragg's law, and you wind up with a dependence which is on tan theta as opposed to 1 over cosine. That means these two parameters can be separated by a diffraction experiment that goes far enough an angle. Typically up in the 80 or 90, more than 80 or 90 degree range. Best would be further on than that. Now, the other thing is about this is that, so what's the resulting shape? Well, not all crystallites have the same size. There's a range of sizes. Some are small, some are large. Small ones give broad peaks, large ones give sharp peaks. That's all then summed over all the ensemble of crystallites. And the resulting peak shape is then a Lorentzian, or can be approximated by a Lorentzian. So crystallite sample broadening is Lorentzian because of that range of particle sizes. And you can make the same argument about microstrain, is that some crystallites will have a lot of microstrain, other ones will have relatively little microstrain. They won't be uniform. And so some of them will be sharp, some of them will be broad because of the microstrain in them. You get a distribution, and that winds up being a Lorentzian line again. So sample broadening is Lorentzian, usually. You can get it to be Gaussian, but only by very, very careful sample preparation that attempts to get all the particles the same size and all of them to have the same microstrain. It's a little hard to do. Some people have managed to do it with gold particles and things like that, but generally not. Okay. Another comment that Joel talked about, which was texture, otherwise known as interesting preferred orientation. Preferred orientation is generally considered to be a nuisance in Rietveld refinement. Texture is interesting because that's some property of the material because of some processing or whatever. If you have randomly oriented crystals, that means any particular direction is found at any kind of angles with respect to the sample. Let's say in a loose powder. Then if you look at the projection of one of these axes with respect to the sample coordinates, let's say up the axis of a cylinder or something like that, and if it's uniform, then all the orientations are equally probable, and this is called a pole figure, which is that stereographic projection. And having it uniform then is a random distribution. If on the other hand, you're looking at something like a wire in which all the crystallites are lined up along the axis of the wire, if the stuff is cubic, then the equivalent axes are also perpendicular, say, in this particular model, to that axis. So you're going to see in the pole figure two features, one of which is a peak in the middle, which is for the ones that are lined up along the wire axis, and a rim around the outside, which is for all those which are perpendicular to it. And it will be a multiple of the random orientation, such that this is a bigger number, and this is a bigger number, and then around here it's going to be less because fewer grains are oriented to give you scattering here. Okay? This kind of thing is described by something called an orientation distribution function. And if you think about it a little bit, it depends on the sample geometry, the sample symmetry, in this case wire texture, as well as the crystallographic symmetry. And I think the next slide shows it. There it is. This is a messy little function. It depends on HKL, and it depends on the direction with respect to the sample. And these are, it's then 4 dimensions. 2 for the reflections and 2 for the sample. So it's a four-dimensional function. A pole figure then is a projection down some y for all the no, sorry, the other way around. It's for a particular HKL and any direction. An inverse pole figure is the other way around. It is down some direction and it's all reflections. So these are just simply two different projections of this function. So what is this thing? Well, first of all, these two guys are spherical harmonics that are used to describe the texture. One of them is associated with the crystal structure symmetry, and the other one is associated with the sample symmetry. So these two guys are both limited by the respective symmetries. Yeah, that one, let's see, H. That one depends on the crystal structure. This one depends on the sample. I got it confused. And so the coefficients, which are then multipliers on these terms, then are either limited by symmetry of the sample or limited by symmetry of the crystal structure. So what do we mean by spherical harmonics? Think atomic orbitals. It's the same functions. You know, S, P, D, F, so forth, except they go to higher order. And the only other thing about them is only the even orders are visible. The odd orders, you can't see them. The Rietveld refinement then consists of these coefficients and three orientations angles that dictate how the sample is oriented on the goniometer. All right. Next bit that goes into a Rietveld refinement is constraints and restraints. And the problem here is powder diffraction data is limited because of the overlaps. And if your problem is too complicated, like a protein, a bit excessive, but like a protein, you have to add additional information in the form of constraints or restraints. Constraints reduces the number of parameters by saying that this parameter and that parameter are related by some function. And it's exact. It reduces the number of parameters by eliminating them. Examples of this are things like you have two atoms on the same site and the site occupancy factors have to add to 1, which by the way is an assumption. That's an example of a constraint. Another one is if you have an atom on a special position, some of the coordinates you cannot refine because it's limited by where it is in the crystal structure, or you can have two of the components be the same, like it could be X, X, Z, or something like that. So those things are constraints. Restraints are the kind of thing where you define an object in your crystal structure that has internal parameters, maybe, and it's fewer than trying to describe the individual atoms with their own X, Y, Z and temperature factors. So what you're doing is, I'm getting a little confused here. What you're doing is that you can say that I'm going to add an extra observation which says this phenyl ring has to be flat. So you add additional information to your problem, which covers the things like the flatness of phenyl rings, or what this angle is between these two CC bonds. You can say what that is. Or you can say what the length of the CC bond is. You say, I know what that bond length is. Let me put that in as an observation. So this is additional information to the least squares. And the whole function then looks something like this with all these restraints. So you have the data, the diffraction data here. You then add in a collection of bond angles that you know what they are, bond distances. Torsion angles, represented as pseudopotentials in GSAS-II. The flatness of planes, non-bonding distances, say van der Waals contact distances. If they're too close, push them apart. What are hydrogen bonds? Chiral volumes is this particular carbon atom right or left-handed, and you can say that, and so forth. And there could be thousands of these things in a protein. This kind of stuff, by the way, is used by single crystal protein crystallographers to do their analyses, to do their refinements of crystal structures, because there's a whole long list of things in which they know what the structures are, and they can use that information. Because after all, they're only dealing with 20 amino acids, and so they know what those are supposed to look like. Okay, intensity extraction, how's that done in a Rietveld refinement? Basically, what you do is you have a particular point in a profile, and you know that here there's 1, 2, 3, 4 reflections that contribute to this particular intensity, say that one. And so what's done is to simply accumulate what the calculated contributions are for that particular point and scale the observed value to that to get the observed contributions for that point. And then you sum them all up at the end after you've gone through the profile and say, okay, well, I've got this set of intensities that contribute to this reflection. This set contributes to this reflection. This set contributes to this reflection, and so forth. The key thing about this is that it's biased by whatever you use for the model to calculate the original calculated structure factors. Okay? And there are 2 algorithms that work not knowing what the crystal structure is. One is a Pauli refinement, in which the values of the structure factors are parameters. This, by the way, then runs into trouble because there are lots of places where reflection intensities exactly overlap. Say here and here and here. You can't tell the intensity contribution from each one of those. So you have to do something to deal with the fact that you've got overlaps. So that makes this particular fitting rather complicated because you have to be able to reduce parameters, get rid of the ones that overlap exactly. Otherwise, the least squares are going to say, no, singular matrix, bang, and you get nowhere. The other algorithm is by Armel-Levi, in which you basically pose a set of calculated structure factors. You then use that to extract a set of FOs. And then you take the FOs and you put them in place of the old FCs, and you just do it again. So it goes around in this little cycle of starting off with one set of FCs, you replace them with a new set of FCs, replace that with another new set of FCs, and you will get a fit, and you will get a set of observed structure factors, which could be horribly wrong because of the overlaps, but nonetheless, it is a starting set of intensities. I'll make a bizarre comment. That's actually an example of chaotic behavior. Everybody know what chaotic behavior is? It's where you have a mathematical function and you say, okay, I'm going to calculate this value, take the result and stuff it back in the equation and repeat. And you get chaos from the resulting xy's. And all those Mandelbrot figures and stuff like that are created that way. So this is actually a chaotic process. It's simple, straightforward. It gets you a result. The parameters in here are simply the positions of the reflections, lattice parameters and other things, the peak shapes, and the background. And the same thing is true of this too, except that this one has structure factors. Okay. Any questions about all that? Because the next thing I'm going to do is an example. A simple example. This is fluorapatite. Why fluorapatite? Well, no particular reason except that Ray Young and his co-workers were interested in tooth enamel and the effect of fluoridation on tooth enamel. And this is what's on your teeth after you've had a fluoride treatment. The apatite is replaced by fluorapatite, which makes it resistant to decay. So he was interested in that, And so he collected this data on his laboratory diffractometer back in the middle 70s, and it has lived on as a Rietveld refinement example ever since. It's been refined thousands of times by thousands of students, both for GSAS, GSAS-II, and its predecessors. Anyway, so how do you do this? Well, the first thing to do is you have to add in the atoms for the crystal structure. Remember, it's a Rietveld refinement is a refinement process, not a structure solution. You have to put in the model. And the initial refinement is always to refine the scale factor, namely with the multiplying factor on the whole pattern, and a background. It always starts that way. And then the next thing to do is you have to actually look at the result and look at the difference curve to find out what's wrong. And it could be all kinds of things that are wrong, because what you're interested in is looking for position errors, shape errors on the peaks, and intensity errors, because each one of those has a different kind of set of parameters associated with it. And this next slide, I hope, gives you an idea what this is about. The position is dictated by things like the lattice parameters, sample displacement errors, not the 0 point, anything that will offset the peak positions. The shape is affected by the instrument, and I'll talk more about that later at some point, or the sample. And the sample then adds on to the broadening that you get from the instrument. So in GSAS-II, these things are all dictated by instrument parameters. And so usually what happens is that the sample peaks are broader than the original calculated pattern. Then the third thing that can happen is you've got something wrong with the crystal structure. Just atoms out of place, or wrong temperature factors, wrong site fractions, whatever. Or you may have missed a systematic correction like absorption or something like that, which affects the intensity of the reflections. These things have different signatures in that difference curve, depending on what they are. If the peaks are in the wrong place, so that the calculated peak is offset from the observed peak, then the resulting curve it goes up, down through 0, and then back up the other side. It's the first derivative curve, okay? Because the peaks are not in the right place. On the other hand, over here, is if the intensity is incorrect, that means that the calculated peak and the observed peak will have the same shape, but different magnitudes. And so that the resulting peak then will look like a peak, a 0 derivative, okay? If the calculated peaks are too sharp relative to the observed pattern, then what you see is a curve that goes up, down, back to 0. And that's a second derivative, and that's because the calculated peak is too sharp relative to the observed peak. So what you see then is going to be these kinds of differences, but unfortunately what you see is a linear combination of them. One of them will dominate, and so that's the one that you have to approach as to what it is that you refine next, because you want the worst thing fixed first in a Rietveld refinement. Don't just simply turn everything on. You'll get rubbish based on experience. The other thing that's important is how they vary with 2 theta. It's sometimes a little hard to recognize that. But depending on the nature of the broadening, for example, remember it's either 1 over cosine or tan theta, and so these have different signatures. But usually people don't worry about that. You just simply refine the parameters and that goes away. But it can be important. Okay, so what do we do next with this? Well, if you look at this, it sort of has the signature of the second derivative, up, down, kind of thing. And so what's probably true is that the peak shapes are too sharp. So you need to vary something that affects the peak shapes, which is the sample probe. The other thing that seems to be true here is that the peaks are slightly out of position And that's probably because there's something wrong with the lattice parameters or the sample displacement. So what we will do next is do the microstrain and include the lattice parameters. And I don't know whether I included the sample displacement or not. But the point is, this is what's true. There's no magic recipe. You have to look at the difference curve and decide what to do next, because you could get surprised. Okay, well, there's an immediate improvement when you did that. Here's the difference curve, and the dominant thing here is wrong intensity. So the obvious thing to do is to refine the coordinates and the temperature factors. And sure enough, it pretty much flattens out, but there is still a lot of stuff left. There's always stuff left in a Rietveld refinement. You never get it completely right. Peter Stevens had the line which I like most about this. A Rietveld refinement is never finished. It's merely abandoned because you just run out of stuff to do. Okay, and so when you're done, you can admire that, and then you can draw a little picture of the crystal structure with polyhedra for the phosphates. And one set of these things is the fluorine, and the other one's the sodium, I guess it is, or whatever it is, calcium. A useful plot to look at is this one, which is the so-called covariance matrix. And when you do the least squares, you'll create a matrix which is full of cross products of derivatives between pairs of parameters with respect to the intensity, profile intensity. When you then invert that matrix, which is part of solving the least squares, then that resulting matrix contains the covariances between pairs of parameters from the least squares. And this is a graphical representation of it. And the colors are such that if the covariance is negative, it's red. If the covariance is positive, it's hard to find one, they're green. The diagonal then, it gives you, in fact, when you look at it in detail, the diagonal is simply the standard deviation of each of the parameters based on these squares. It's square, actually. And so you can zoom in on this and look at the details of it. And you see up here, these are background parameters, and there's always a high correlation there between pairs of background parameters. So that's not really a problem, but just be aware that's what that is. The thing to beware of is white bands, and if you sort of look at it, you'll get nan, which is not a number. And that means that the least squares has detected a singularity and removed the parameter, or got choked up on. Okay? So it's useful to look at that. And with that, I thank you for the first talk. Any questions? Hmm?
30 minutes to lunchtime, but you can take over a bit more if you want.
Okay. Well, I've got another talk here.
Yes.
Okay. I have to get rid of this one.
Where's the restroom?
Give people a couple of minutes.
You want a couple of minutes washroom break or something? We have that. And then start the GSAS before.
Hurry back. hurry back.